Buenas tardes a todos y a todas, estimados colegas, estudiantes, en representación del Departamento de Química y de la Facultad de Ciencias de la Universidad de Chile. Es un honor introducir o presentar a un investigador destacado. El doctor Wirth es profesor de Química Orgánica en la Universidad de Cardiff. Él obtuvo su doctorado en la Universidad Técnica de Berlín. Luego de una pasantía doctoral en la Universidad de Kioto, en Japón, el Dr. Wirth trabajó en la Universidad de Basel. En el año 2000, el Dr. Wirth logró su posición oficial, ¿cierto?, en la Universidad de Cardiff, donde actualmente es académico. Ha publicado más de 170 artículos científicos en distintas revistas con un alto índice de impacto para la comunidad científica. Su trabajo ha sido citado más de 7.000 veces, alcanzando un índice H de 48, basado a partir de los datos registrados en Web of Science desde el año 2000. Su perfil ORCID registra más de 230 trabajos, donde se incluyen tanto sus publicaciones en revistas, capítulos de libros y otros. Ha recibido distintos premios. En el año 2000 de la Sociedad Química, la nueva Sociedad Química Suiza, recibió el premio Werner, y en el año 2016 fue galardonado con otros 2 premios a partir de la Royal Society of Chemistry. ¿Cuáles son las áreas de interés del Dr. Wirth? La estereoselectividad, las reacciones de estereoselectividad, transformaciones oxidativas con yodo hipervalente. También trabaja mucho en lo que es la investigación de mecanismos de reacción y la síntesis a través de procesos electroquímicos utilizando microreactores. Good afternoon, dear colleagues and students. On behalf of the Chemistry Department and the Science Faculty of the Universidad de Chile, it's an honor to introduce an outstanding researcher. Dr. Wirth is professor of organic chemistry at Cardiff University. He got his PhD at Technical University of Berlin. After a postdoctoral stay at Kyoto University in Japan, Dr. Wirth worked at the University of Basel. In 2000, Dr. Wirth took up his current position at Cardiff University. Dr. Wirth has published more than 170 scientific articles in different journals with a high impact on the scientific community. His work has been cited more than 7,000 times, achieving an H index of 48 based on Web of Science data since 2000. Dr. Wirth's ORCID registered more than 230 works, including journal articles, book chapters, and others. Dr. Wirth has been awarded with the new Swiss Chemical Society with the Werner Prize in 2000, the Wolfram Research Merit Award, and the Bader Award from the Royal Society of Chemistry in 2016. In the same year, he was elected as a fellow of the Learned Society of Wales. Dr. Wirth's main interests of research concern stereoselective electrophilic reaction, oxidative transformation with hypervalent iodine, reagents including mechanistic investigation and electrochemical synthesis performed in microreactors. Professor Thomas Wirth, thank you very much for visiting our faculty and contribute with your experience on our academic community. I would like to extend a warm welcome to our distinguished guest. Le queremos dar una calurosa bienvenida a nuestro invitado.
Well, thank you very much for the very kind introduction and for also allowing me to come to your university and talk a little bit about the chemistry we have been doing well, over the last 15, 20 years in Cardiff. Now, the title of the talk is probably slightly incomplete. I will not only talk about iodine reagents in synthesis, I will also talk, and you mentioned this already, about electrochemistry and electrosynthesis, and at the very end I will talk a little bit about enzymatic synthesis, an area which we also have pursued in flow chemistry together with a colleague of mine. Now, before we start going into the details, you can see, and you can see hopefully soon, you can see here the laboratory from Justus van Liebig in Germany, and this is almost 200 years ago, right? And you can see it's a very crowded lab, and you can also see that there are some flasks on the sideboard, some retorts. So devices which are still nowadays used in synthesis. Batch type chemistry is something which chemists have done for a very long time and are still doing this very, very successfully. We have all the equipment to do reactions in a flask. What I like to show you is that one not necessarily needs to perform reactions only in a flask. There are also other methods to perform reactions, and these flow type reactions can have some advantages, and I'll point out some of those advantages to you and demonstrate how we can use flow chemistry advantageous in synthesis. So here you can actually see a schematic scheme how batch chemistry works. We take two molecules, A and B, and put them in a flask, and that's what you all know. We add some solvent, we then start stirring for a while, and after a certain amount of time, in this case, the reaction product C can be isolated and obtained from the flask. Now, important in flow chemistry, the chemistry does not change at all. So the molecule A and the molecule B still react to the same product C. The only difference is that they are both being dissolved in a solvent at the beginning of that flow system, and then we typically need a pump in order to pump those solutions through the flow reactor, which can be a long tube. And if again we choose the dimensions of this tube correctly, which means the residence time in the tube is the reaction time, then after exiting the tube, we again can only isolate the product C. We have the advantage that we can regulate reaction conditions much more precisely in these flow systems. So, for example, temperature and pressure can be adjusted very precisely, much more precisely than in a flask, which can be big, and if you heat a flask on the outside, clearly the temperature in the very inside might be different. And that's different in a tube. And the main physical difference between a tube reactor and a batch reactor is the surface to volume ratio. So we can perform reactions, and I already mentioned, due to this surface to volume ratio, the heat exchange in the tube reactors can be very good, and so we can maintain the temperature. I also like to mention the safety aspects of that system, which means we can generate hazardous materials, or we can use dangerous compounds in the flow system without exposing danger to the person operating the system. I will also show you a little later in the talk that these microreactors have very good mixing capabilities, so the solutions can be mixed very rapidly, which can actually be very beneficial. and we can even synthesize large amounts of compounds using the flow reactors, because we can not use only one flow reactor, we can use 2 or 10 or 100 in parallel and still make large amounts of reaction products. That's again demonstrated here. If you want to scale up a batch process, typically from the lab scale to a pilot scale where you synthesize kilogram amounts, and then to a production scale where ton amounts are being made, often reaction conditions have to be modified, and you cannot use the same reaction conditions for a ton production with the reaction conditions you developed for a gram synthesis in the lab. So in the flow reactor, and that's again shown here with a very simplified scheme, the numbering up of the reactions, which means not using only 1 or 2, but 10 or 100 of those flow reactors, can achieve large amounts of materials, or alternatively, you simply leave the reaction running for a long time, and then you can collect large amounts of reaction products. So again, here's the schematic scheme of a flow reactor. We have 2 components, A and B. They are both transported with pumps through the flow reactor. We can add a quench solution which stops the reaction at the exit of the flow reactor, and then we can isolate the product C from the reaction mixture. I also want to introduce the iodine chemistry, because I will start with some of the iodine chemistry we have been investigating. Now, those reagents we are interested in are hypervalent iodine compounds, and here you can see actually the guy who made the first hypervalent iodine compounds, Konrad Wilgerod, and he synthesized the dichloroiodobenzene by reacting iodobenzene with elemental chlorine, so you can make the iodine-free derivative here. And not only iodine or the dichloroiodobenzene, also other hypervalent iodine reagents have become quite interesting and important in organic synthesis. You can see some of them on that slide here. Quite well known is the desmartin periodinane, which is a very mild oxidant to oxidize an alcohol to the corresponding carbonyl compound. And because it's a mild oxidant, it tolerates many other functional groups, and so is frequently found, for example, in natural product syntheses. So if you want to use those hypervalent iodine compounds, you have to make them first. And you typically make them by oxidizing an iodine-1 compound to an iodine-3 reagent. And that's actually shown here at the very top. And there are different oxidants established for making these transformations, and they are listed on the left side of the slide. So you can see sodium perborate, a classical oxidant to oxidize iodine-1 to iodine-3, but also peracids can be used, select fluoxone, other iodine-3 reagent, oxygen. There are many different oxidants which can oxidize an iodine-1 to an iodine-3 compound. Now I will show you that we can also use electricity to oxidize an iodine-1 to an iodine-3 species, and then use the iodine-3 reagents in synthesis. Now, before doing that, I like also to show you that we quite early on actually looked at chiral hypervalent iodine compounds. And if you have a chiral reagent, you can do a stereoselective transformation. And here you can actually see one example of those reactions. So we use these hydroxy tosyloxy iodoarine derivatives, and here you can see a stereocenter, and attached to the stereocenter is a methoxy group, and the oxygen of this methoxy group can coordinate to the hypervalent iodine atom, thus providing the iodine with a chiral environment. And so you can actually also see the X-ray structure on the right side of the slide, where you can actually also see the close distance between this oxygen atom and the iodine. So the electrophile here, the hypervalent iodine electrophile, is now a chiral electrophile, which means we can now do a reaction, in this case with a double bond, in a stereoselective way. The iodine electrophile now adds to the double bond, forming this iodonium ion, and then the nucleophile, in this case a tosylate ring, opens and forms this intermediate here. Now this intermediate is quite an interesting intermediate, because now we have a hypervalent iodine moiety, so an iodine 3 atom attached to an sp3 hybridized carbon atom. And this means this iodine moiety is an excellent leaving group. It's a so-called super leaving group, and you can actually see rate constants here. These have not been determined by us, but by other people, and so in relation to a chloride or a tosylate, these hypervalent iodine moieties are excellent leaving groups, which means that they are replaced immediately by a second nucleophile. So the second tosylate now enters here, displaces the iodine, and we get these bis tosylates as reaction products. And because the hypervalent iodine electrophile is chiral, we can observe some selectivities in this bis oxytosylation in this reaction product. Now those were the first chiral hypervalent iodine compounds which we investigated in this reaction. After that, several other research groups have looked at other chiral hypervalent iodine compounds, and here's one which is quite well known nowadays. This was introduced by some Japanese researchers, and this now is a hypervalent iodine moiety which has two stereocenters, one on the left and one on the right side, and the stereogenic unit on both sides is a lactic acid. So a quite cheap stereogenic unit, so you can make these hypervalent iodine compounds quite rapidly. And we now use the hypervalent iodine moiety to attack this double bond here, and now it is not an intermolecular reaction as with the tosylates on the previous slide. We now have a nitrogen and an oxygen nucleophile both close to the double bond, and so we do a cyclization reaction to give us these isourea derivatives as the reaction products. And again, the more complex hypervalent iodine compound now sets up a new stereocenter, and we have optimized this reaction to good yields and selectivities, and then we can even cleave the isourea moiety and liberate the corresponding amino alcohols, which are very good substrates as ligands or as building blocks in organic synthesis. Now, we have also looked at other double bonds which can be functionalized using the hypervalent iodine electrophiles, and one is shown here. We can generate these silyl enol ethers out of the ketones, so we deprotonate and silylate, and then we even add a nucleophile onto the silicon atom, and then we expose this double bond here to the hypervalent iodine electrophile. This gets activated, and then the nitrogen nucleophile attacks, and we can then directly form the corresponding alpha functionalized carbonyl compounds with a new stereocenter in the alpha position. The two trimethylsilyl moieties on the nitrogen, they are lost in the aqueous workup, and we can directly obtain the alpha amino ketone as the reaction product. Now we can not only add nitrogen nucleophiles, we can also add oxygen nucleophiles, we can generate quaternary stereocenters, and we can even synthesize new chiral amino acids if we choose the correct starting material. So those are applications of these chiral hypervalent iodine reagents. And another application of these hypervalent iodine reagents is, and I mentioned it already, they are very good leaving groups. And if they are very good leaving groups, they can leave behind a cationic species. And with cationic species, or with carbocations, you can perform rearrangement reactions. And that's what we have done. And before showing this, here's another example of an intramolecular cyclization now with an external sulfur nucleophile. So we can add one nitrogen and one sulfur atom to a double bond, and we can also add two nitrogen atoms, and this is now again a cyclic, bicyclic reaction product where we add two nitrogen atoms, and again we can make diamines now as reaction products using these chiral hypervalent iodine compounds. Here we have developed a new hypervalent iodine compound, and remarkable here is we don't need to preform the hypervalent iodine compound. We can use the iodine 1 derivative and add a stoichiometric amount of an oxidant. So we make the iodine 3 compound in situ. The reaction is occurring, and then the iodine 1 is back oxidized to the iodine 3. Now here's the example I was referring to. This is the rearrangement reaction we investigated with hypervalent iodine compounds. This rearrangement reaction was in principle known. The iodine electrophile now again activates the double bond here. The nucleophile, in this case trifluoroethanol, adds and ring opens. And now this iodine moiety is a very good leaving group. The cation here gets stabilized by the adjacent phenyl system in forming this phenonium ion intermediate. And this phenonium ion intermediate then gets ring opened here, and we form the corresponding acetal as the reaction product. And you can see the phenyl group migrates from this carbon atom to this carbon atom here. We have labeled the molecule with a deuterium atom, so we know that the phenyl group is migrating and not the acyl group on the other side. And you also realize that in the reaction product there is a new stereocenter being formed, and so we can use chiral hypervalent iodine compound for a stereoselective rearrangement. And again, we have optimized this reaction, and here you can see we get 95% yield, 97% EE of this rearranged reaction product, again with a new stereocenter here. So after we have published this work, it was quite interesting to see that other researchers picked up this idea of a stereoselective rearrangement induced by chiral hypervalent iodine compounds. And that's what you can see here. This is the reaction we have reported, and then Jacobson looked at slightly different starting materials. They used these unsaturated amides as substrates. They also changed the nucleophile. We used the alcohols. They used fluorides as nucleophile, and they also looked at a catalytic version, so 20 mole% of the iodine 1 compound and stoichiometric MCPBA as the oxidant to prepare the iodine 3 compound in that reaction, and they get, again, good yields and selectivities, and then have also looked at the computational modeling of these reactions, showing that the two side chains in the aromatic, on the aromatic iodine derivative are forming a chiral moiety where the substrates or this double bond then approaches from one side only and induces the stereoselective rearrangement. Now, before I now come to the formation of hypervalent iodine compounds using electrochemistry, let me very briefly introduce electrochemistry, in this case, flow electrochemistry to you. Now, in electrochemistry, you basically have two electrodes which you put in a beaker for an electrolysis. Now, flow electrochemistry is more or less the same, with the difference that the two electrodes are much closer to each other, and as you can see here, we use a pump to pump the solution which is being electrolyzed through that gap in between the two electrodes, and while the solution is being pumped through that gap, it is being electrolyzed, and as soon as the solution exits this gap, it's no longer electrolyzed, and we can collect the product in the collecting flask. Now, this idea of these flow electrochemical devices is not new. This has been around for quite some time. You can see here several examples of these flow electrochemical devices which have been reported in the literature. Yoshida from Kyoto University was one of the first ones reporting a device, and all those devices operate the same principle. So you have two electrodes, and in between the two electrodes there is a gasket, and in this gasket you have cut out the reactor channel, and if you sandwich this together, then the bottom of the channel is one electrode material, the top of the channel is the other electrode material, and the distance between the electrodes is simply the thickness of that gasket material, and so you can perform the electrochemistry while flowing the substrate through that gap in between the two electrodes. Now, what is also important to know is that in batch electrolysis, you typically need to add additional electrolytes to the solution to have sufficient conductivity. In the flow electrochemistry, this is often not really required because the distance between the electrodes is so small that there is sufficient conductivity in the solution, and you do not have to add additional electrolytes to the reaction mixture. So we developed a second generation reactor, which was then also commercialized, and that's now a device which we have been using to make hypervalent iodine compounds. And here you can see that we can follow classic protocols. We can oxidize the iodoarine here and then use a different arine to make these diaryl iodonium salts. And this reaction was actually performed with one of our very first microreactors, electrochemical reactors, which was quite small in volume, and so we couldn't produce large amounts of the diaryl iodonium salts. And then later we thought, well, we probably should also synthesize some more practical hypervalent iodine compounds, such as diacetoxy-iodobenzene. And when we initially tried this reaction, you can see we miserably failed. We only get 25% of reaction product and some side reactions. And the reason why we only saw 25% product is that the product, the diacetoxy-iodobenzene, was insoluble, almost insoluble in the reaction mixture of acetic acid and acetonitrile. And that's always bad news for flow systems. If you produce solid compounds, they crash out and block your reactor. And that's why we got low yields. And so the solution to this problem was we needed a solvent system which dissolves the reaction product so that it does not crash out and block our reactor. The solution was to replace the solvent system, acetic acid acetonitrile, with either trifluoroethanol or with hexafluoroisopropanol. In this solvent system, the reaction products, the hypervalent iodine compounds, are soluble and do not block our reactor. The difficulty here was that the reaction products which we make here are unstable. You cannot isolate them. They are stable in solution, but they are unstable in substance, so you cannot isolate them, and that's why all those yields here are NMR yields. They are not isolated yields. But this didn't bother us a lot, because we can actually use this concept of making a hypervalent iodine compound in the electrochemical flow reactor in solution, and then using it directly in a second reaction. And that's shown here, so we can make the iodine-3 reagent in the electrochemical reactor. This is unstable, but we don't isolate this. We can add a substrate and then directly obtain the reaction product. And here you can see we have done various reactions. We added different substrates, so we can do lactonization reactions, cyclization reactions, alpha oxytosylations, carbazole formations. Those are all reactions which are quite typical for iodine-3 reagents. But what we can now also do is we can add acetic acid as a substrate here, and the acetic acid now exchanges the trifluoroethanol ligands on the iodine with an acetate, and so finally we can make the diacetoxyiodobenzene in good yields. And if we use other substrates here, other substrates to exchange the ligand on the iodine, we can also synthesize different hypervalent iodine compounds in good yields, and they can now be isolated and used in other reactions. So what we were also interested in is a special class of hypervalent iodine compounds. Those are hypervalent iodine compounds which have two fluoride atoms on the iodine, so iodine-3 difluorides. And those are very interesting reagents because you can use them for fluorination reactions. And fluorination reactions is a very hot topic in synthesis. Introducing fluorine atoms in reagents, in reaction products, is very important. The traditional synthesis of these reagents requires HF. There was also some electrochemical synthesis already in the literature, and we thought, well, if we look at a flow synthesis of these reagents, then we can again make the reagent and directly use it in a subsequent reaction. Now, while we were undertaking these investigations, there were two papers appearing in literature, one from Waldvogel and one from Lennox. So Waldvogel synthesized the iodine-3 difluorides electrochemically from 4-iodotoluene, and then the double bond here gets cyclized. A fluorocyclization towards these heterocycles was reported, while Lennox fluorinated double bonds and got the difluoride as reaction products. Now, both of these reported procedures were batch protocols, so they added electrolysis to get the reaction products, which caused quite long reaction times, as you can see here, and related to that is quite small or low productivity of these compounds. Now, we, as I said, were interested in developing a flow protocol for this process, and here we take again 4-iodotoluene as a reagent which is oxidized to the iodine difluorides in the electrochemical flow reactor, and then we add the substrate. This reacts here with the reagent. We can then even add an aqueous workup so that the excess fluoride is destroyed and nobody comes into contact with the fluoride. We get an aqueous waste and can isolate the reaction product in the organic solvent. So we optimize this reaction and then could show that we can actually perform the same reactions as Waldvogel and Lennox could perform in batch. We could perform in flow. And here you can see that we can perform fluorination reactions of double bonds. You can also see, well, probably not at the very back, it's quite small printed, the yields of those reactions are very similar. The batch and the flow protocol, with the difference that the flow process only takes 10 minutes, while the batch protocol takes 2 hours for the reaction to complete. So we are much faster in the flow process. And the same is true for these fluorocyclization reactions. Again, very similar yield, sometimes a little bit better, but 15 hours in batch, 35 minutes in flow. Also for the difluorinations of double bonds, which we also investigated, quite illustrative is the fluorination of ketones, 24 hours in batch, 1 hour in flow at 55 degrees. So again, similar yields, but in flow, much faster reactions. Now, due to the reaction setup, we can, however, now also functionalize substrates which you could not functionalize in a batch system. In the batch system, you always electrolyze also the product. If the product is oxidation sensitive, it gets degraded and you will never be able to isolate the product. And that's, for example, the case for this compound here. In a batch process, you cannot make that molecule because it simply gets degraded and oxidized in the batch reactor. In the flow reactor, we make the compound outside the electrochemical reactor, which means it does not is not being degraded, and we can isolate 62% yield of this particular compound, and there are different others which we can also isolate and make in a flow system, but which are inaccessible in a batch protocol. We can even use more functionalized materials, and we can also leave the reaction running for a long time. And so if we leave the reaction running for 10 hours, we can make 8.5 grams of the reaction product quite easily. So that's a real advantage of the flow electrochemistry. And then we thought maybe we can now also use a chiral hypervalent iodine compound to make stereoselective fluorinations electrochemically. And I was quite happy that our student performed this reaction first, a reaction without the iodine catalyst. And here you can now see that there is a background reaction. Even without the iodine catalyst, we get almost 40% yield of the difluorinated reaction product, which means even with a chiral iodine catalyst, we will not be able to see large selectivities of stereoselective reaction, simply because of this background process which is operating all the time. So we had to look for a different reaction which can be performed stereoselectively, and this is the reaction we found, which is the fluorination of these beta ketoesters, and the fluorinated reaction product is shown here. Again, we optimized the reaction conditions, got reasonably selectivities and yields, and could also demonstrate that other substrates work in this reaction, which is the first electrochemical and stereoselective fluorination process, which is currently also being expanded to other syntheses. So we could show that we can perform fluorination reactions using the iodine difluoride, and here's one example where we could show that we can also perform dichlorinations using the hypervalent iodine dichloride. And we used a very similar process, so we made the iodine dichloride electrochemically, so we made this unstable reagent with the 2-hexafluoroisopropanol ligands, and then we can exchange one after the other with a chlorine ligand, and we can make the iodine dichlorides, which now can add to the double bonds of the alkenes, providing us with these dichlorinated reaction products in good yields. Now here are only 3 examples reported, but I think we have made 25 or 30 different dichlorides from the corresponding alkenes. Now I told you about fluorinations and chlorinations. Clearly I need to talk a little bit about brominations, but In bromination reactions, we do not need an iodine catalyst because, as you all know, if you generate small amounts of elemental bromine, the elemental bromine will directly react with a double bond. We don't need any activation or catalyst. And here we make small amounts of bromine electrochemically from hydrogen bromide, and then in the presence of an alkene, we can directly perform dibromination reactions, or if there is a little bit of water present, we can also generate the corresponding bromohydrines, but that's not a new reaction. This is a very old reaction which has been done many, many times. Now, the interesting feature of these flow electrochemistry is that it can be automated. You can computer control the whole process. You can have an auto sampler which takes a starting material, puts it into the pump. The pumps flow the mixture through the electrochemical flow reactor. We can add an analytical device, and then we can even add a fraction collector which collects the different reaction products after the reaction process. And so we don't need any manual operation for carrying out these reactions, and so we used a fully automated system for reactions, and some of them are summarized here, so we can perform selenulations of phosphine oxides, as you can see here, which gives rise to these reaction products. We can even add 3 different starting materials, an alkene, a diselenide, and an alcohol for performing an alkoxyselenylation of the alkene, or we can use sulfides as starting materials, and then depending on the current we use, either synthesize a sulfoxide or a sulfone, or in the presence of the cyanoamine, we can also make sulfoximines as reaction products in this process. And for example, this last one here, all those examples, 69 examples, they can be synthesized in about 3 days. I should actually say 3 days and 3 nights, because these automated systems, they also work at night, and so you just program them, come back the next morning, and you can isolate your reaction product. So very easy to operate, and you can synthesize large amounts of materials and different materials without actually being present in the lab, which is quite a nice feature. We also have synthesized chiral hypervalent iodine compounds electrochemically. This is one example here. It follows exactly the same protocol which I have already shown you. So we can make those compounds, and then we have used a spirolactonization reaction to develop this process, and you can see a couple of examples of this methodology. Now, to finish off the iodine reagents, more recently we have synthesized new lactate-based iodine compounds. You might remember the 2 chiral lactate moieties in the reagents I have shown you were both attached via an oxygen atom to the aromatic ring system. And so we have now changed one of the oxygen atoms to a nitrogen atom, or changed both of them to 2 nitrogen atoms, or have only 1 chiral moiety on one side. And so we have synthesized and characterized a series of new hypervalent iodine compounds, and then also looked at the reaction, or at some reactions using these new hypervalent iodine reagents. And we mainly looked at the alpha oxytosylations of these propiophenone derivatives, now again in a catalytic way, so we use only 10 mole% of the aryl iodine metachloroperbenzoic acid as the oxidant, which, as I have shown you, we can also replace by the electric current, and now got reasonable selectivities, sometimes very high yields, and so that's actually an area where we are still working on, and we have actually already surpassed 60%. I mean, I think we are now in the order of 85% enantiomeric access for some of those new chiral hypervalent iodine reagents. Now, I also mentioned at the very beginning that mixing is an important aspect, and here you can actually see that mixing is also an important aspect when you drink your cup of tea or coffee. If you pour milk in your cup of tea or coffee, you generate initially a concentration gradient. So you have high concentrations of milk and high concentrations of coffee. And that's exactly the same if you pour a reagent in a big flask, right? You have high concentration gradients, and if you use, for example, an organometallic reagent, you cool the reaction down to low temperature so that there is no side reactions due to this large concentration gradient. And if you stir rapidly, it typically takes time until you remove the concentration gradient and then can drink your cup of tea or coffee. The same is true for this reaction, which is shown at the bottom here. That's one of the reactions which we develop in collaboration with Professor Allemann at our university. He is a specialist in terpene cyclases, so enzymes which take this farnesyl diphosphate and make a cyclization to a terpene reaction product. And you can see if you stir this rapidly in batch in a flask, after 1.5 hours, you get 35% yield of the reaction product. And the reason is that this enzyme, which is being used here, is product inhibited, which means the terpene product sits in the active site, and you need to remove it by stirring rapidly with an organic solvent so that a new substrate can be turned over. And what we then thought is we might use a microreactor for this extraction, for this rapid mixing. And so that's a microreactor we have made very early on. There are 2 inlets here, and if you introduce 2 immiscible liquids in these 2 ports, then you form this so-called segmented flow. Here in this video you can actually see these solvent segments traveling along in the capillary. And the solvent segments do not only travel along in the capillary, there's also an interaction between the solvent and the channel wall. And due to this interaction, there's a very strong internal vortex mixing in each of these solvent segments. And so it's not only a very strong mixing in each of the solvent segments, there's also a very strong exchange at the interface in between the 2 immiscible liquids. And so we use this rapid exchange at the interface for accelerating reactions. We could show that we can accelerate organic reactions, but here I show you that we can also accelerate these enzymatic reactions by this very rapid extraction. And so we use an aqueous solution of the enzyme and the buffer and the substrate, and then we simply use pentane to extract the reaction product from the active site in the enzyme. And so we can now synthesize these different terpenes if we use different enzymes in much higher yields. And we then also optimize the reaction conditions using some design of experiment approach where we looked at the ratio in between the organic and the aqueous solvent. We looked at the reaction time and the diameter of the tubing, and this all plays a role. And so you can see here exactly the same reaction time, but now we see almost quantitative yield of the reaction product simply by this rapid mixing of the enzyme or rapid extraction of the aristolochine terpene from that reaction. Now I want to emphasize also the terpene which is at the bottom here, which is amorphadiene, because amorphadiene is a direct precursor for artemisinin. Artemisinin is the #1 drug to treat malaria, and so it's a very sought after compound, and we got some funding from the Gates Foundation to look at the process, a flow process of cyclizing FDP to amorphodiene, and then using a couple of chemical steps to synthesize the drug molecule. Now here you can see only very briefly what we did. We used the amorphodiene for a hydroboration oxidation sequence, so we convert this double bond into an aldehyde. This is dihydroartemisinic aldehyde. This is a known compound, and this compound now needs to be treated first with singlet oxygen to cleave this double bond here, and the dialdehyde then needs to be treated with triplet oxygen. So this oxygen bridge is being introduced to form dihydroartemisinine, which can be used as a precursor to other drug molecules or as a precursor to artemisinin. So I think I only like to show you this hydroboration oxidation sequence which we developed in a flow system. And so by starting with the amorphodiene, we performed the hydroboration with 9-BBN, and the 9-BBN we also made in the flow system, starting from octadiene and borane. So here we make the 9-BBN, which now reacts with this double bond here. We then do an oxidative workup, so we generate the corresponding alcohol as the reaction product, and then use a hypervalent iodine reagent to oxidize the alcohol to the aldehyde, and so we can synthesize dihydroartemisinic aldehyde, and you can see the production rate here is also quite good, 1.5 grams per hour. The reported yield for the batch system is almost comparable to the flow yield. However, the batch protocol takes 2 days until you reach this product, and here we get this in I guess 30 or 40 minutes. So very fast synthesis of these intermediates to artemisinin, to the malaria drug. What you can also do, and this now almost brings me to the end of the talk, you can also support enzymes on a solid material and then use these solid supported enzymes in a packed reactor and flow the substrate across. Now that's what we have done here. We have used this enzyme either in solution, or we put it on a solid support and put it in a packed bag reactor. And so we do get the cyclized reaction products in reasonable yields, and the polymer supported enzymes, they are slightly less reactive than the free enzyme, but the amount of enzyme you can immobilize is quite small, which means you can also only generate quite small amounts of the reaction products. We can analyze them, but we will never be able to make gram amounts of reaction products using this immobilized enzyme technique. And so we thought, well, if we can't immobilize the enzyme, we better leave it in solution and mix rapidly in solution. And so we used a new technique for mixing in solution. And the technique is very briefly explained here. It's coming from the countercurrent chromatography, and you can use 2 liquids for chromatography. You use one liquid as a stationary liquid or a stationary phase, and one liquid as a mobile liquid. And that's shown here. So the blue liquid is the stationary phase, and then we use the red mobile liquid to flow across, and we can use this for separation or for extraction reactions. And the device which is used is this high-performance countercurrent chromatography. This tubing here, this coil is now on this bobbin here. This rotates around its own axis and also around the central axis. And while doing so, it creates areas of settling where the 2 liquids are pushed away from each other through high G forces, or we have areas of high mixing where they are mixed very rapidly. And this mixing and demixing is occurring many, many times, depending on the rotation speed here. And here you can actually see one of those devices operating in our lab. So here's the bobbin which rotates, and it rotates around the central axis and performs this mixing, demixing method very rapidly. And here you can see now again the same enzymatic reaction I already showed you, but performed either in the batch system, in the segmented flow system, or in this HPCCC system with the rapid mixing and settling. And so typically we do get better yields in the HPCCC system, and so we can reduce the reaction time with the enzyme to just above 10 minutes, and in one of those runs we can generate 30 to 35 milligrams of reaction product, which is now already something you can isolate and you can work with. And if you leave this reaction now running for a longer time, you can also make 200 milligrams if you simply leave it running for 10 times of the time. There was, however, one problem. The problem was the access to this starting material. You still need to feed the enzyme farnesyl diphosphate. And the farnesyl diphosphate, I'll come to this in a second, how we make the farnesyl diphosphate. Here's just an example that we can also use other enzymes, esterases, and accelerate esterases using exactly the same methodology. And here's now the problem which we have, because we need to make the FPP chemically. So we take farnesyl, make the bromide, and then exchange the bromide to this pyrophosphate moiety. And you can actually see this is a very bad reaction. 2 days requires lyophilization, and the yields vary between actually 0% and 50%. So sometimes you just get nothing, and sometimes you get a little bit, sometimes you get a little bit more, but that's not satisfactory for a good way of accessing the starting material for all our enzymatic syntheses. And so we and Professor Hallemann thought maybe we can even make this starting material using enzymes. And here's how they actually developed this process. They took isoprenol and prenol as the two starting materials, and then a set of kinases which can actually attach a phosphate to the isoprenol and to the prenol, and then a different kinase which can attach another phosphate to make the pyrophosphate. So the pyrophosphate from isoprenol and the pyrophosphate from prenol, and now we use a farnesyl diphosphate synthase, another enzyme which now combines those two molecules to make FPP. And if you use the mixture of those enzymes, you can do this in a batch system. Almost, well, you get quantitative yields after 16 hours of stirring these enzymes and starting materials. 16 hours is again quite a long time, and we thought now, well, maybe we can even do or synthesize the FPP starting material in the flow system by simply introducing all those enzymes into the flow system. And that's what we did. So here we use the two starting materials, isoprenol and prenol, the mixture of the enzymes, and we make FPP here. Add farnesyl diphosphate and make FPP here, and you can actually see with a segmented flow technique we get also quantitative yields in 6 hours. But nobody tells us that we need to isolate this FPP. We can synthesize the FPP already in the presence of the terpene cyclase, and if we do that, then we can perform the whole enzymatic synthesis starting from prenol and isoprenol and those enzymes. So we make FPP, we add the terpene cyclase. The terpene cyclase now cyclizes FPP to the terpene reaction product, and that's what we isolate. And here we now use the cubebol synthase, making cubebol a different terpene product, and you can again see a comparison between batch, segmented flow, and now using the HPCCC as the key device for the rapid mixing, and we can access these terpenes now in a very short time and very efficiently. We don't need to synthesize the FPP in substance. We just ask the enzymes to make this FPP for our synthesis. And so we can use this methodology now with different terpene cyclases to make different terpene reaction products. And here you can just see a selection of the terpenes we have made together actually with the amounts which we have isolated from these reactions. And so different terpene cyclases we have used, different terpenes are being obtained, and all in reasonable yields and in reasonable quantities, so that we can now use them for subsequent reactions if we wish so. So I guess this brings me to the end. I just like to show you that we can use flow synthesis as a very advantageous method in synthetic methodology, exemplified by some hypervalent iodine chemistry, where we make unstable compounds and then add the substrate and get the reaction products. I showed you we can make the difluorides, electrochemistry in general as a very useful tool for preparing new organic compounds. And I should not close before thanking the people who were involved in that work. So I like to thank my group very much for their hard work. Also the funding agencies, which you see in the bottom, to provide some funding for us for doing that research. And I do not want to close before showing you where Cardiff is actually located. So this is the main building of Cardiff University, and we are quite lucky. Main parts of chemistry, the chemistry department, are in this main building. Cardiff is located about 2 hours west of London. It's the capital city of Wales. So this is Cardiff University, and this here, Prysgol Cardiff. This is also Cardiff University, but in the Welsh name. And I'll finish with Dor o Far Ian. This is also Welsh and means thank you very much.
Thank you very much. Tan impresionados.
I don't know how to explain, but this can easily help to create quantum computation.
Pardon me?
This process can help to create quantum computing.
What can help quantum computing?
Yes, the process of creation of these molecules.
I'm not sure what you understand by quantum computing.
You are trying to boil specific compounds. If you can select this compound, you can create a structure who can make qubits.
Now I think the idea of our synthesis of molecules is not to to arrange them in a type that the molecules contain information. I think we are more synthesizing the compounds because of their biologic effects, such as the use in the synthesis of drug molecules or so. So we do not really tend to use them as, let's say, information storage, which you would need to if you want to do quantum computing.
And in the first part that you show, I see that you make this structure to generate electricity. And I see a cathode, this receptor of a specific energy. And that's how you build a computing processor. And this actually is very difficult to do in lab. But in the way that you show the selection of specific particles, the construction of these buildings, is gonna make more easier. And no sé cómo decir estable, de la estructura.
I guess the reaction we perform is indeed performed between electrodes, but the size of those electrodes is quite big, right? So it's 25 square centimeters, 5 times 5 centimeters. And for, I guess, computing, you need to miniaturize these things if you want to transfer electrons and then maybe even reuse those electrons for other processes. And that's what we have not invented. But there might be people who are looking into these type of chemistry processes in order to store information. Yeah.
Yes, actually, I saw a video of in Spain. These people are trying to make these selectors, but for computing, and in this case. But it's not an easy way to do it.
Yeah.
They can. They are using little particles or elements of Cooper, in this case, to recept the energy, the 1, 0.
Yeah.
Like.
Yeah.
So, if organic, in an organic way to create
Yeah, I think I understand what you mean. Maybe we can discuss it after the lecture in more detail, right? Yeah, yeah. Thank you.
Thank you. Yeah.
Los invito a preguntar en español si prefieren y yo les traduzco la pregunta.
Si puede hacer la traducción,
Sí.
por favor. Primero agradecer la charla y me gustaría preguntar si pueden ocupar cualquier enzima para generar reactores de flujo o si requieren alguna característica enzimática principal para poder generar estos reactores. Si las han probado con otras aparte de las que ya mostró en la publicación.
The question is if, in principle, you could use any enzyme in these reactions.
Yeah, I think you probably can. I only showed you briefly that we can use esterases in the same way. I think you might have a problem if you use an enzyme which is extremely slow. So very slow enzymes probably can't be accelerated enough that they produce sufficient amounts in that device, because the residence time or the reaction time in the overall system is only half an hour or so. So if you use too slow enzymes, then this might not be useful. But in principle, we are not restricted with regards to the enzyme. However, the enzyme needs to be more or less stable in the presence of an organic solvent, because we mix it with an organic solvent all the time, right? And many enzymes, or several enzymes, start degrading, denaturing in the presence of an organic solvent. And so that's a difficulty. You will not have the enzyme with exactly the same activity after that reaction. So we can recycle the enzyme a couple of times, but at some point there's not much activity in the enzyme left.
Más preguntas.
In an electrochemical cell, you have two reactions,
Yes.
and for you it's useful just one. What happened with the second reaction? Do you have problems? Because many times you can have a loop, a sequential reaction, and
Yes. I mean, that's a very good question. Clearly, we have the reaction at the anode and we have the reaction at the cathode. And I didn't talk about the hydrogen production, which is on the other electrode in our case. So typically, what we do have is hydrogen generation, just the proton conversion to hydrogen on the other electrode. Sometimes you can also have the reaction of your product on the other electrode, and that's when some electrochemists then use a divided cell, right, where they divide the anodic and the cathodic reaction through a membrane. This also has been done in flow systems, and we have also tried that, but that's experimentally much more difficult and challenging to operate than an undivided cell, and so we prefer the undivided cell. Yeah.
thank you.
A mí me gustaría plantear una pregunta también. I would like to ask about the difluoroiodonium compounds.
Yes,
They are very highly oxidizing.
yes, yes, yes.
How could you react substrates that are easily oxidized to direct the reaction towards fluorination?
Substrates which are easily oxidized.
Yes.
Yeah. Well, I mean, if they are oxidized easier than fluorinated, then they get destroyed, right? That's what I guess those are intrinsic reactivities. If you expose them to the hypervalent iodine difluoride, then they get destroyed. You can try and modify the oxidation potential of your reagent using maybe different solvent systems, different reaction conditions, and if you lower the oxidation, but maybe substrates can then be fluorinated rather than destroyed, right? Yeah.
Thank you. I wondered about compounds where you have the iodine bonded to one fluorine atom and something else.
That's a good idea. We do know only for few compounds that we do have the iodine difluoride, simply because we have an X-ray structure, right? But what happens in solution, we can't really tell, right? I mean, there might be compounds reactive which have only one fluoride ligand and the other one has been dissociated off, right? And you actually need a ligand to dissociate off to have the reactive site on the hypervalent iodine for attaching a substrate, right? Yeah.
¿No hay más preguntas? Bueno, le agradecemos al profesor entonces su charla y sus respuestas.
Thank you very much. Yeah.
I want to give you this list of the university.
Oh, oh.
Can I
Yeah, please.
I will use this.
Yeah, just can you put it through? Yeah.
And now you have the University of Chile.
Wow. Thank you very much. Thank you.
Quiero agradecer la participación de todos ustedes, a los estudiantes de pregrado, que han tenido un primer acercamiento a la investigación de un investigador destacado. Así que muchas gracias por la participación. Pueden pasar a tomar un café y conversar con Tomás o con cualquiera de nosotros en este momento. Así que muchas gracias por asistir. Tomás, thank you very much.
Thank you.
Aquí no va.